Okay, today we are going to talk about motion in 3 dimensions. In actually 2 dimensions and 3 dimensions, 2D and 3D. And specifically, we're going to look at what are called Cartesian coordinates. And this is a topic that you're all, I assume, a bit familiar with from your various courses. Okay, so in the previous lecture, we talked about motion in a straight line. Here we are going to talk about motion not in a straight line, but in 2D and 3D. So what do we mean by this? So here's a representation of motion in 2D or 3D. So let's say we have these coordinate axes, x, y, and z. And we have a point P, which is denoted by the coordinates x, y, z. And these coordinates are basically called Cartesian coordinates. And we can have a vector like so. Let me erase this and redraw it, actually. Let me put the point somewhere else. Let me put the point out here so that it is not an extension of this line. So you want to be careful drawing a picture because sometimes the picture might be unintentionally misleading. So let me draw this vector. And this vector that goes from the origin to the point P is often denoted by R. That's an R. Okay. And that is called a position vector. Okay. So OP is R. It's called the position vector. And if you define unit vectors j, I, and k, so I, j, k, we have the position vector equal to xi plus yj plus zk. Okay, so that's the position vector. So that vector defines essentially the position of this point as it potentially moves around in 3D space. So you can imagine this point moving around in 3D. And as it moves around, we track how x changes as a function of time, how y changes as a function of time, how z changes as a function of time, and that describes the movement of this particle. Okay. Moving along. So let's say that particle is moving. We can define the velocity, which is basically dOP divided by dt, the derivative of this vector, which you can write as dr by dt, okay, which is basically d by dt of this thing, okay, which is basically dx by dt I plus dy by dt j plus dz by dt k, okay. So here's something subtle. So we are differentiating each of these terms to get this expression. This is velocity, right? This is velocity. Let me move this here and say this is velocity. This velocity of point P equals the rate of change of this vector, which is the rate of change of r, which is just putting that in here. And that's this thing. Going from this to this, we are making an assumption here, okay? We have to use chain rule because there's a product of two terms here, x and I. If you recall chain rule, d by dt of two things is like if you have x times y, or A times B something, recall chain rule. D by dt of, let's say, P times Q, where P and Q are two variables, is basically dP by dt Q plus P times dQ by dt. Okay, so that's how you do chain rule of differentiation. Okay, and if we apply the chain rule of differentiation to this vector, we should ideally get dx by dt I, and then another term which is x times di by dt. And we don't have terms like di by dt, dj by dt, dk by dt, because why is that? Why don't we have di by dt, dj by dt, dk by dt when we differentiate this? Okay, it's because exactly these vectors are actually fixed vectors. These vectors are basically constants. It's not just numbers or scalars that can be constants. Vectors can also be constants. So these vectors are basically constant vectors, by which we mean their direction is fixed, their magnitude is fixed. These are unit vectors, right? I, j, k are unit vectors, and their direction and magnitude are fixed. Therefore, when you do d by dt of I, it's basically 0. Okay, so note di by dt equals dj by dt equals dk by dt equals 0, because constant vectors. This superficially sounds a bit obscure, but you will notice in the very next lecture, we will actually look at unit vectors that are actually changing in time. So that when you differentiate those unit vectors from the next lecture with respect to time, it turns out they are not equal to 0. So you do have to use this expression, but in this Cartesian coordinates, you just have this simplicity. Okay, moving along. So that's velocity. This is velocity, and we can write an expression for acceleration as well, which is identical essentially, or analogous. Acceleration of p equals basically dv by dt. We are going to write use the notation v for this, for velocity. You want to be careful, and I try to be careful, but it's not always possible perhaps. Unfortunately, by convention, we use the letter R here and then the letter V here. They look sort of similar. If we write R a bit not very carefully, it will start looking like a V. So you want to be careful. And hopefully we can also deduce this from context. But these are unfortunately historical standard notation that people have been using for hundreds of years. So I suppose we want to use that unless we don't want to do it at some point, I guess. But for the purposes of this course, we will use this notation. R for position vector and V for velocity. Acceleration is dv by dt, which is A, is the notation that we use. And of course, that's also equal to d square R by dt square, the second derivative of the position vector. And it's of course going to be equal to d square x by dt square I plus d square y by dt square j plus, I'm going to write that here, d square z by dt square k. Okay, so that's going to be acceleration. We are going to continuously use the following short form, which some of you may be familiar with, but if not, no worries. So this is notation alert. I suppose all this is also notation alert. All of this is notation as well. But notation alert, we use when we say dx by dt, we can write that as x dot, right? So this is the dot notation. Dot, oops, represents one derivative. Okay, a dot represents one derivative. Two dots represent two derivatives. So x double dot would be represented, would represent basically d square, d square x by dt square, etc. So okay, two dots represent two derivatives, and so on. And usually dots represent derivatives with respect to time, okay? We usually represent derivatives with respect to time using dots. If it's derivatives with respect to position or something, we don't use dots, okay? This is just historical convention. Okay, so for instance, we can write some of this stuff in terms of the dot notation, where we can just say v equals x dot I plus y dot j plus z dot k. Okay, so that, for instance, is fine. A equals x double dot I plus y double dot j plus z double dot k. So that's totally fine. Okay, so that's Cartesian coordinates. That's the basics of Cartesian coordinates. And again, we go from R to V to A via differentiation. And then we go from A to V to R via integration. Sometimes people, instead of writing x double dot, y double dot, z double dot, we might use the notation ax I plus a y j plus a sub z k. So this is a subscript, just to be very clear, this is subscript. Similarly, we might write this as vx I plus vy j plus vz k. And basically each of these terms, vx is x dot, vy is y dot, vz is z dot, right? So it's just notation. This is the velocity in the x direction, this is the velocity in the y direction, this is the velocity in the z direction. Similarly, this is the acceleration in the x direction. This is just notation, okay? And these things you can do component by component, this integration and differentiation. So we can do differentiation or integration one component at a time, I guess. Okay, so for instance, we can go from a sub x to v sub x to x itself, or by integration. And we can go from x to vx to ax by differentiation. Okay, this is just an example. Any questions about that? So the next little piece is finding components of vectors. So if finding components of a vector along a direction given by unit vector n. Okay, so what do we mean by this? So given some vector b, some vector, its component along n is given by b dotted with n. Okay, that's the expression. So the geometric interpretation, if you are curious about it, is basically if you have n, the unit vector, and b is this some vector, and the component is basically the projection of b onto this direction. Okay, so that's basically the component. Projection meaning you drop a perpendicular from the endpoint of b onto n. That's called the component. In any case, it's good to know what that is. We will leave that aside for a minute. So that's component. Another quantity is the magnitude of a vector. Magnitude of a vector, if the vector is b with components bxi plus byj plus bzk, the magnitude is given by, the notation is b, like so. Sometimes you also use this double vertical bars. This is just notation for the magnitude, and the magnitude is equal to square root of bx square plus by square plus bz square. Okay, magnitude just means length of the vector in this case, and the length is square root of the sum of squares of the components. Why is this true? Why is the length equal to this? Where does this come from? Okay, so it comes from Pythagoras' theorem. The magnitude is like a hypotenuse, and these things are, you can show that the length is basically the sum of squares of the three individual sites, I guess, or three individual components. Okay. Okay. Sort of generalizing Pythagoras theorem to 3D, I suppose. Okay. If you want to know the unit vector along a vector B, unit vector along B. So we have some vector B, let's say, and we want to find the unit vector along that vector. What is that equal to? You take the full vector and divide it by the magnitude, and that's the unit vector. Okay, so it's B divided by magnitude of B, that's the unit vector. So basically bxi plus byj plus bzk divided by square root of bx square plus by square plus bc square. Okay, so these are the main set of notations / formulas for Cartesian coordinates. And then once you master this basic notation, get good at this basic notation, all that remains is basically integration and differentiation to go from acceleration to position or position to acceleration. And the methods are rather similar to what we did for 1D, except we now do this in 3D. So this is actually something that I wrote, but it's sometimes true. We can sometimes do integration or differentiation one component at a time. It really depends on if this is a function of time, then you can do this one component at a time. But if it's a function of velocity or position, as we did in the first lecture, then we may be able to do the integration if the three directions are decoupled. In other words, the motion in one direction does not affect the motion in the other directions. So in those cases, we will be able to treat the components independently. But if the motion in one direction does affect the motion in another direction, then all bets are off. You have to do very often a numerical integration, basically solving the equation using a computer. Okay, that's a slightly more advanced remark. We will come back to that, I suppose. Okay, so that's the end of this sort of theory section for Cartesian coordinates, and we will now see a few examples.